back off and probably forget. So, right. The red button is red is what you want.
If red is on, then everything.
Yeah, fine. Okay. Yeah. So what I did is I described to you a little bit about how you do these lattice calculations, and just to show you that we could do calculations of physical quantities, masses, in for a gauge theory, a four-dimensional gauge theory. I gave you one example, which I'll show you again, just to remind you of this. Here's a correlation function on a lattice with quite a small lattice spacing, SU3 in 4 dimensions. And and you're doing the correlation function is a sum of exponentials, each exponential coming from a particular eigenstate, energy eigenstate. And at large t, you expect a single exponential, and that's so you're looking for the lighter state, which gives you that single exponential at light t, which dominates at large t. Which dominates at large t. This is the number of time lattice spacings. And what you see is that you can find operators which give you a very good overlap onto the lighter state, so that you have a single exponential early on, and that enables you to do calculations of masses at the sort of percent level. So that's just to convince you that, by a specific example, that you can do calculations accurately, reasonably accurately on the lattice. So that was at a particular lattice spacing, and that was one particular mass. And as you see here, the result necessarily is going to give you the mass in lattice units. So what I know, this is e to the minus an energy times time. The time is in lattice units, a times a certain number of lattice spacings. What I'm counting is my lattice spacings. And so what I extract when I fit this numerically is the mass in lattice units. And I get the mass, in this case of the scalar glue ball, as being this particular value, but it is in lattice units. So far, that is nice, but not, you might say, very useful. The one thing it does tell me, actually, until this point, I didn't know what the lattice spacing was in any units except its own, which is 1. But now I know what the lattice spacing is in physical units, in terms of the mass gap in the theory. The lattice spacing is 0.33 divided by the mass gap. So that's already some useful information. In particular, of course, as I go to the continuum limit, where a goes to 0 in physical units, I will expect this number to become smaller and smaller. Okay, so that's one useful bit of information. Obviously, I can now calculate some other mass. I could calculate, for instance, a tensor glue ball, spin 2 glue ball. Then I take the ratio of the two values I get. The lattice spacing drops out, and I get a dimensionless ratio. And that now is a useful quantity. It's still not the continuum limit, because it's a calculation done at a particular value of the lattice spacing, a value of the lattice spacing where a times m is 0.33. So I need to extrapolate to the continuum limit. So the next step is to do that. And here's just a statement about how one does that. So I take two masses that have calculated one value of the lattice spacing, and at any given time, I don't really know what the lattice spacing is going to be. I have this parameter in my action, up multiplying the action, which, as we saw, is the inverse Baire coupling of the theory. So I do know that as I go to the continuum limit, because it's an asymptotically free theory, the Baire coupling will go to 0, and therefore that parameter beta will go to infinity. So all I know is as I increase that parameter, the lattice spacing will become smaller. But for in any given calculation, when I choose a particular value of beta, I don't a priori know what the lattice spacing is going to be in physical units. So what I do is I'd actually do the calculation of several masses and take ratios. Now, the ratios I will focus on here are actually masses of, at this point, of masses of glue balls divided by the square root of the string tension. I haven't yet discussed about how I calculate the confining string tension. I'll come to that in a moment. But let's suppose I've done that. It'll be done in some very similar way to the way I calculate glue balls by some suitable correlation functions. But let's suppose that's been done. And so I extract a mass and the square root of the string tension in a way I showed you just now from some correlation functions of that kind. Take the ratio, the lattice spacing drops out, There is still, of course, some lattice spacing dependence of this ratio, but we know something about that once the lattice spacing is small. Because when the lattice spacing is small, because the theory is asymptotically free, the coupling becomes smaller short distances, you can trust a short distance, you can control a short distance expansion. And this was done a long time ago by Symanzik, where he discussed how the lattice action can be written as the continuum action plus higher powers of A times other effective actions. And the leading correction you expect in this analysis when you do use the kind of action we're using here, the simple plaquette action, is that it should be order A squared. So what you expect is that the mass ratio should be given by the continuum value once the lattice spacing is sufficiently small, plus A squared, plus, of course, higher powers in A squared as well. So, so I write this, in this particular case, I choose to use sigma to make up dimensions here, the string tension itself. So what you do is you've done your calculation, you take the ratio, and then you take the correction to be some constant times the value of the string tension you've calculated, and you do a fit to A squared sigma equals 0. And there may be, of course, higher order corrections, but those initially you ignore. I should mention that although another thing that I will ignore, as we all do actually in the field because it's a good approximation, although I've written down here a constant, it's not actually a constant. When you do this analysis, it's a power series in the coupling in G squared. So this is really a power series in G squared here, but G squared varies only very little over the region of lattice spacings where I do my calculation, because it's varying logarithmically with the lattice spacing. And therefore, I will treat it as a constant. I mean, ultimately, if you do calculations which are incredibly accurate of these mass ratios, you would have to start taking into account the fact that this it's not just a constant, it's a constant plus something times G squared plus something times G to the fourth and so on. But at this point, we don't need to. So that's going to be the way we go to the continuum limit. We do a series of calculations at different values of this parameter beta and calculate the mass ratios, calculate A times M, which tells us how small the lattice spacing is, and then plot the mass ratio against, for example, in my case, I decided to do it against A squared sigma. So here is the mass ratio calculated for various different, in about 10 calculations here for different lattice spacings. And what you want, you start off with a coarse lattice spacing here, where A squared sigma is quite large, and you're going down to where A squared sigma is very small, and where you want to go is to A squared sigma is 0. And you believe the leading corrections of order A squared, so we're looking for a extrapolation which, at least for small A squared, is a straight line. Now there are two sets of points here. These solid points are for the scalar glue ball, and then up here you've got the tensor glue ball, the lightest tensor glue ball, which you can calculate in a similar way using operators which have non-trivial rotation properties, so that your correlation function, in your correlation function you get states which have only states which have non-trivial rotation properties. There's some subtleties and things one could discuss about the fact that that one needs to discuss about the fact that the lattice has only got 90-degree rotations, so you're talking about the cubic group rather than continuous rotations. So there, but I won't go into those subtleties. So let's just call this a spin 2 glue ball here, and this is the scalar glue ball. Okay, so you can see now that it looks as if you've got a pretty controlled continuum extrapolation. If you do an extrapolation, you can do it with approximately 1% error here on both of these guys. There are certainly visible lattice spacing corrections on the 0++, less visible than the 2++. Even if you go to coarse lattice spacing, you get pretty much the same value. So that's nice, but not necessary. You can extrapolate from something that's varying as well. And so that's nice, and it's very particularly nice for SU3 because you can go to quite small lattice spacings on big lattices and get very close to the continuum limit explicitly, so the extrapolation is very well controlled. Now, you might ask yourself, what is, we've assumed that we just take an A squared sigma correction. Suppose we included an extra correction, A to the fourth sigma squared, what would happen? Well, in that case, if you take an A squared just an A squared sigma correction, you can't include these points. This is the straight line here. So you drop off the values of the coarsest lattice spacing where you expect that the higher order corrections are going to be larger. And so if you can't fit them, you just drop them off and fit the points that you can closest to the continuum limit. That's a perfectly valid procedure, sensible procedure. However, you might worry about estimating the error That's what you might call a systematic error associated with not including higher a squared corrections. And if you do include an a to the fourth correction, then you can go through this point. You have an extra parameter, and then you have this line. And as you see, because your points go up quite close to the continuum limit, there's essentially a negligible difference between these two extrapolated values. So in SU3, it's very nice and well controlled. I'm now going to show you a similar plot for SU8, where things are not quite so well controlled. And the reason is simply that the calculation is slower. And the main factor in slowing down the calculation is, of course, that you've got n by n matrices that you're multiplying together in your calculation rather than 3 by 3. And the number of operations in multiplying matrices together is essentially n cubed. So when I go from SU3 to SU8, I'm essentially slowing myself down by a factor of 8 divided by 3 or cubed, which is about which is about what? Is it about 20 or something like that? Anyway, something of that kind. So it's about 20 times slower. So what does that mean? It means that in practice, I can't use such large lattices. I don't go to a 32 to the 4 lattice. My largest lattice is a 16 to the 4 lattice. But I still want my 16 to be 1.5 Fermis across, so as not to have finite volume corrections that are significant, which means that I don't go to such a small lattice spacing. I go to a lattice spacing which is twice as large. And in terms of a squared, that means I'm 4 times as large. So I only go up to about here. And I do an extrapolation from further away. So that's a little bit less controlled, but it's still reasonably good. And of course, one can improve this systematically by using more computer time, if you like. So here is the SU8 calculation. It doesn't go up so close to a equals 0, but it looks very similar in many other respects. The tensor glue ball still shows almost no lattice spacing corrections. The scalar glue ball shows more marked lattice spacing corrections. And if you try to do just an order a squared extrapolation, you can do that certainly. Here's no problem at all. Here you have to drop these points, and then you can put your lines through these points and end up here. And that's what I give you here. But then if you try to do add an order a to the fourth correction, you can actually go through all these points very well, but you go significantly below in the continuum limit. And let's look at that more closely. If you do this extrapolation here with these points here, they're all quite accurate, and you get a small error, 3.53 with an error of 0.08 for the continuum value. And if you do this higher order fit, because you've got one extra parameter, there's a bit more slop in the fit, you've got larger errors as a result, and it turns out to be 3.13 with an error of 25 here for this intercept. However, the important point is not so much the fact that this error is larger, but the difference between these in units of this quoted statistical error here is about 5 sigma plus or minus 3, because this is 3 times 8. So really the difference between these two extrapolations is 5 plus or minus 3, the naive statistical error. And this is an example where you have to worry and try to estimate systematic errors, because they can be much larger than your statistical errors. And they usually follow from the fact that you've made some assumptions. And these assumptions, like the assumption that I only need an order a squared correction, is a perfectly valid approach, but we'll have to worry about the size of the errors quoted as a result. So this is an example where one has to worry a little bit. And having said that, just to warn you about that, the plot I've got actually ignores those fits and just tells you what happens if you use the linear fits, which is pretty good. All the qualitative conclusions I'm going to give you are not affected by that. However, if we were actually comparing with some theoretical model which was extremely precise and wanted numbers to a few %, then we would have to worry about it. But here then, let me give you now the comparison, what happens at different n to these two mass ratios. So we're now addressing the question of whether n equals 3 is close to n equals infinity directly in this plot. So we expect, when we go to large n, we expect by the usual counting arguments that correction should be of order 1 over n squared. And so the reasonable way to plot these mass ratios is against 1 over n squared. because then the leading correction is a straight line, and it's easy to visualize in this kind of plot. So here are the values for the spin 2 glue ball mass of the spin 2 glue ball divided by the square root of the string tension, and for the scalar glue ball. And what you see here are values of SU2, SU3, SU6, SU8. This is probably SU4. Yeah, this was SU4. 2 values for SU4 for reasons I won't go into. And what you, never mind whether, now, this is the SU8 value, and you saw that if I'd used a higher order fit, it would have gone down a bit and actually would have looked better on this kind of plot. Probably this would have gone down slightly too, although we go to weaker, smaller lattice spacings for SU6. So really, there is some slight systematic error on these extrapolations, but nonetheless, what you do see here is that SU3 and SU infinity are very close to each other, reasonably close to each other. So this is an example of what one finds is that for characteristic quantities, obviously not for all quantities, but for the simplest quantities in theory, same is true of the deconfining temperature, a number of other quantities, simple gluonic properties, SU3 is already actually pretty close to SU infinity, just on the order of 10% differences. So that's the coefficients that you see here of the 1 over n squared are not large. In fact, here it's very small for the tensor glue ball, but for the scalar glue ball, it's this coefficient here is half the value of the leading term. So it's
Is it a generic phenomenon that the correction looks smaller for the higher spin or higher excitation states?
well, so I don't know. I mean, I don't know because we don't have many of those states actually. So I can't tell you.
Do have, is that a
Well,
pattern?
there is a but it's got higher errors. I don't think I can address that question usefully. And also, this comes back to another question, well, to another issue, which I sort of mentioned then said I wouldn't discuss it, which is the fact that we've got a rotation group which is 90 degrees rather than a cubic rotation group. So if you're trying to talk about spin 4, for example, it becomes subtle and tricky. You're talking about things that don't fall into irreducible representations of the cubic group. Just, there's not a one-to-one correspondence. Essentially, the J4 state gets split up in various representations of the cubic group. And this has been addressed, but not in the context of large N. And I hope it will be addressed in the context of large N. It will be very interesting to do much better. The calculations that have been done of the glue ball spectrum in this kind of comparison between low n and larger n is very limited at this stage. It's sort of really preliminary calculations in a sense, although they are 3 years old, one hasn't gone beyond that. So it really should be done better. One needs an accurate, much more accurate spectrum, including excited states, but we don't have it, so I can't really answer that question usefully.
In fact, the corrections are 1 over n squared and not some other power. It's Toft scaling, but that's also something you see from your
Well,
plots. Is that right?
these quantities are not accurate enough to say that, actually. If what I did is I made that 1 over n to some power, that correction, and then tried to fit that power, I would get some constraint, but not terrific. It turns out if you go to 2 plus 1 dimensions and calculate the string tension there, then you do constrain it enough to get something which is, the correction is 1 over n squared. You can say definitely, pretty definitely. Here the accuracy is not quite good enough.
As opposed to 1 over n.
As opposed to 1 over n. But that's, yeah. So in 2, and I will be in 2 plus 1 dimensions possibly later on, at some point in these lectures. But in 2 plus 1 dimensions, of course, you remember that g squared has dimensions of mass. So you can calculate root sigma over g squared n, and you expect that to go to some constant value, to be equal to, as a function of n, to be equal to the something which is the n going to infinity limit of it, plus you can fit that with c1 over n to the alpha. And the alpha is really, if you assume it's integer, it's 2. It can't be anything else. It's certainly not 1, it's certainly not 3. Of course, if you allow it to be fractional, then with a numerical calculation, you'll get just some error which encompasses 2. Yeah, I think that's okay, so that's the first thing we can do. Now, let me take a step back and say something about linear confinement, because the other issue we wanted to address, and that brings me to, I just want to say something about calculating the string tension. The string tension before I leave it, maybe I should make one comment, since every now and again experiment is mentioned. In SU3, if you look at this value, this sort of extrapolated value, 3.47, the statement is that in the continuum theory, the scalar glue ball is 3.47 times square root of sigma. If you take a value for the string tension that you believe you have in the strong interactions for either from the slope of edge trajectories or from heavy quark potentials, you think it's around 450 MeV. The string tension, square root of the string tension is around 450 MeV, which means the lattice glue ball is around 1.5 GeV. So the lattice calculations have for a long time been saying that the lattice glue ball in SU3 is going to be around 1.5 GeV. Of course, if there are nearby in mass or in energy QQ bar mesons, flavor singlet QQ bar mesons, it will mix with them. Now, so the current phenomenology situation, as I understand it from the people who do these things, is that indeed there is strong evidence that there is a glue ball around 1.5 GeV. This evidence is kind of complicated, and it's complicated by the fact that there are other flavor singlet QQ bar mesons in the neighborhood, which are scalars. So there is this, so that if you like, the smoking gun here is that what you expect with the QQ bar mesons is a nonet, an octet plus a singlet in the usual SU3 flavor. And what you find is that you've got not just the two singlet pieces, the one in the octet and the nonet, but in the nonet, but you have a third one. There are three. So this seems like reasonably good evidence where you have an extra state, which is flavor singlet, and people have been trying to determine, how these three states are mixed pieces of the strange, anti-strange quark, or the UU bar plus DD bar, and the glue ball, how they mix. So there are people doing that kind of thing. But I think that there's good, although not totally convincing evidence to everybody that you do have a glue ball in that mass region, scalar glue ball. And part of the reason that this situation doesn't get resolved, I think, very quickly, is that there hasn't been really much in the way of new experiment in that mass range. People haven't been, but I think there are plans to have some more new experiments in the mass range. In certain small machines that are being constructed here and there. And if they do, with very high statistics, it might clarify this whole business of the low spectrum, including maybe up to the tensor as well. But without some new experimental data, this is always going to be floating there as it has for 10 years as a strong possibility, but no certainty yet. Okay, so that's as far as the experimental situation with glue balls is concerned. Let's get back to the string tension. So if I want to calculate the string tension, there are various ways I might proceed. The simplest way, obviously, is to take my two static sources a distance r apart. So the operator, and calculate on the lattice the lightest energy of such a system. And the operator you would use would be, that's for my source, you would have a product of links joining them, and then, sorry, this would be phi 0, say, and phi r. So you join up from 0 to r with a product of links, which is just in the continuum, that would be path-ordered exponential joining them. When you do a gauge transformation, you get a gauge transformation here, which cancels this gauge transformation here from points position r, which cancels this, so this is gauge invariant. You look at correlators of these guys, you look at correlation functions of these guys in time now, just as you do for the glue balls. So you do a correlation function of this operator with a conjugate operator at a later time. This is a static source, and well, there's some freedom here, but the typical thing that you will get from that is just itself a straight line in time. That's a propagator for an infinitely massive particle in the fundamental representation. So you've got, at one time you've got this thing, at a later time you've got this thing. You integrate over the phi's and let their mass go to infinity, you get the straight lines here, and you've got yourself the Wilson loop, actually. So this is the Wilson loop. And this is why the Wilson loop gives you its expectation value is related to the potential, the heavy quark potential. So you have here T to R, and if T goes to infinity, you will get some number times e to the minus V of R times T. terrible notation because this looks like temperature. At this point, this is time. This is the extent in time. But then let me make it small t. So I take an r by t Wilson loop, take its trace, expectation value, and at large times it goes like this. And so you can extract the potential. And you can see whether the potential goes for small r, much less than lambda QCD. You would expect it to be just the Coulomb term. If you're in 4 dimensions, that will be running coupling over r with a Casimir factor here, which for SU3 will be minus 4/3, but in general there is the Casimir of the fundamental. And then at large r, of course you don't know in advance, but there's a lot of suspicion that you have linear confinement, and lattice calculations do indeed show that. So you expect sigma times r plus there can be a constant term here, a divergent constant term from here, from the self-mass of these guys, but I'm ignoring that. And here what you would have is some corrections. And if at large distances, this is behaving like a simple bosonic string, with just the massless modes being those of the transverse oscillations, then this will be minus pi d minus 2, the sort of central charge term, over 24, I believe, yeah. And then there are plus possible L times R, 1 over R. Yeah. So this is what you, this is the kind of behavior you would be looking for. And typically what one finds is that one can just add these two together. Well, let me not say that, but there's some confusion there. So this is what you expect at large r, this is what you expect at small r. And indeed, that's what you find in lattice calculations. There's good evidence for that now. Very, very accurate calculations of that kind of thing in SU3. So this is one way of calculating the string tension.
Lucia term on the lattice? You get that coefficient?
You will. I'll show you how accurately you can get the Lucia term, actually. That's one of the things I want to go into. Yeah. But you do. There's now very good there is good evidence that the coefficient is indeed that you expect from a simple bosonic string theory. And in 2 + 1 dimensions, as I show you, have extremely accurate evidence for that, I think.
That term would change if there were internal degrees of freedom.
If there were massless internal. So this is determined by the massless degrees of freedom on the string. If there are massive ones, then that's a different story, which I was talking about in the curriculum, but you know, we'll talk about before as well. So that's a different story, an interesting story. And that's one of the reasons for actually, what I want to go on to after this is to discuss not just the lightest string, but also excitations. Because that will, and compare that to the simplest expectations you have from, say, a free string theory, and then you see deviations from that, and that begins to tell you something, although one has to interpret it, and I'm not quite sure how, you know, that's not trivial, but there are deviations, so that'll be interesting. So this is one way to calculate it. You calculate the potential. Now, it so happens that if you're just interested in strings, this is not really purely a string. There's a Coulomb piece here. There's and somewhere a string forms at larger r, at smaller r you don't have a string, at larger r you have a string. If you are truly ambitious, you would say, well, maybe I should be able to get everything from the string theory. So I don't care about that. I'm going to sort of do it all. But I, at this point, being less ambitious, we want to have a setup where we're just looking at the stringy part. So to do that, we remember that our space is finite. It's torus. So you can imagine taking your sources around and annihilating them off each other, and then just being left with a string. So what I want now is an operator that will just project onto the string. Well, you can see the operator I've used here is this guy going between the sources. Instead, I can use the same operator going around the torus. So this is a spatial torus. If it was a time-like torus, you would have called it a Polyakov loop. It's just a Polyakov loop, the holonomy that we've been hearing about. So from Shiraz. But it's actually so I've got this Polyakov loop traced around the torus, and that will project onto loops of flux around the torus if we're in the confining phase. If we're in the confining, if the theory becomes deconfined, that can break. Those strings can break. Then you will project onto the vacuum and other states as well. But if you're in the confined phase, what you will have is you will have a spectrum that you can calculate of loops around the torus. So that's what I've got here. That's what I want to calculate. So here we are. Here is a space, Euclidean time, and I'm going to be, here's a Polyakov loop, here's a conjugate Polyakov loop, and I calculate the correlation function. I have the same kind of expression I had for correlation functions in general. It's a sum of exponentials, and each exponential comes from an energy eigenstate, and all the eigenstates in the confining phase will be closed loops of flux. Some of them will be excited closed loops of flux, and so on. So that's kind of set up. It's nice because there are, of course, no Coulomb terms, but it's nothing produce a Coulomb term as you had with sources. So for this particular issue, it's a rather clean setup. Now, there is a difference, of course, although there are no Coulomb terms at short distances, so I can make the string as short as I like. Actually, at some point, I am no longer able to make it any shorter without going through a phase transition. So there is a phase transition, finite volume phase transition, as I shrink the spatial torus, this particular spatial torus, keeping all the other tori large. And this transition is actually, apart from just, if you just rename axes, you see that's just the deconfining transition. I called this space, and I called this time, Euclidean time, but I could have, it's Euclidean, I could have equally well, at this stage, call this time and call this space, and then I see that, and then I know that what I've set up here is a finite temperature system. If I call this time, it's finite temperature with respect to the other the spatial volume now using the other three directions. And I know that as I decrease this spatial length to 1 over Tc, I encounter a deconfining transition. And for large n, as we'll see, it's first order. So it's a sharp, very strong first order transition. So beyond that, you no longer have a string there winding around here. So there is a shortest length to which you can discuss the string spectrum, which is essentially given by 1 over Tc. So I can't discuss arbitrarily small strings. Okay, so let me then present a little bit of evidence that just one slide there's other slides I could have shown to suggest that at larger n we still have linear confinement, and here is the slide. This is a calculation of the lightest energy of a string wound around a spatial torus, where I vary the size of the spatial torus. So that means I have to, of course, do a separate calculation for each different spatial torus size, and here it is. Here is the mass as a function of L. In lattice units, it's done in SU6 at some value of the lattice spacing. What you see here is that you do seem to have a linear rise approximately. There are clearly corrections to it, and in fact, as we'll see later, these can be approximated well by the string theory corrections. So that looks roughly linear rise, so that's good evidence now that we still have linear confinement in SU6. And of course, there's one thing you always have to be careful about is that you are really looking at long distances. You don't want to be looking at short distances. Now, what does long mean? Well, the characteristic scale of a string is given by the square root of the string tension itself. So what you want is L times root sigma to be reasonably large out here, where we see this approximate linear rise, in order to be convinced that it's asymptotic, rather than being just some subasymptotic phenomena. So if you can at least do that consistently, self-consistently, you address that question by saying, well, if I fit this in order to get a string tension, how big is this L in units of the string tension? And it turns out that L root sigma out here for this point is about 5. So that's quite large. I think that's one can be confident that one's looking here at an asymptotic behavior. Okay, so this is the kind of numerical evidence you have for confinement continuing at large n. Now, it's always possible, of course, that the string tension, as we go to larger n, would be going to 0 in units of other masses. But we've already seen that doesn't happen. And we've seen that in the plots of m root sigma, for example, that I showed you just a moment ago.
Question,
show that. Yeah.
Do you have any way to determine the width of the string? And you would think it's 1 over root sigma, but there may be n corrections.
Yeah, I mean, that's a harder calculation, but people have done that at various times, occasionally coming up with controversial results. But so I haven't done that. No, not directly, no. I mean, roughly speaking, one can kind of see that it's, in some sense, its intrinsic width is of order 1 over Tc. But that's to say, if I have an hour, I was considering strings that go around a short torus. If instead I take a string, so here's my short torus, and instead if I construct, and I have a long torus here, and instead if I construct a string that's here, and look at its energy as I shrink these size, I find that there's no very significant finite volume corrections to the string energy until it gets to be around, until this size is about 1 over Tc. So, so that's roughly speaking. I mean, there's always a slight ambiguity about talking with a string. It is a quantized object, and it's got fluctuations on it, 0-point fluctuations, as well as having some kind of intrinsic width that one thinks of classically. However, if you have any fluctuations, you know, on a torus, you don't really meet yourself. You don't overlap as long as you're sort of wider than the intrinsic width, even if there are big fluctuations. So, so that's why I'm being a bit hesitant in talking about the width. But I think, broadly speaking, one can say that it seems to be a 1 over Tc. On the other hand, so there are 1 over n corrections in Tc itself, which would apply to this statement. However, I wouldn't want to make it so, you know, I'm less sure of the accuracy of this statement. One can't really say, I mean, it would need rather more different kind of calculations to really address that question.
So if the width was something like 1 over n times 1 over Tc, you'll have no way of...
Oh, no, sorry. I thought you meant 1 over n corrections to 1 over Tc.
No, I meant
no.
correction to the actual width.
I don't think I would be, no, I don't think it is. Well, that's an interesting question. Is that a possibility in some approaches? I don't know. I don't think so.
I wouldn't have thought so.
No. I mean, in the simplest models, it will be very hard to imagine that, because if you just think of a bag model where you have flux going through, and it's just the total flux, electric flux, electric flux going through, and you're calculating E squared, you divide it uniformly over the width of the flux tube, and then you calculate it by integrating over the area. If you shrink the thing, I think then the string tension will diverge. I mean, if you make it narrow, because the field gets stronger, you get a sort of E over R all squared times R or something. So, well, I'm not saying this right, but you find you will get a divergence if you shrank it to 0.
I think the same kind of phenomenon is visible in ADS models as well, where the string droops in as far as the kind of the boundary imposed by confinement.
No n.
Well, you know that's the large N, and that's the large N picture. So I don't think there's any reason to believe that the flux tube would shrink to order 1 over n size when the n goes to infinity.
I think some of these stories that people were spinning with the domain walls and super Yang suggesting that perhaps the string. You know as well as I do.
There was one lattice result recently at the last lattice conference where someone was claiming some extremely anomalous behavior for the width of the flux tube. I didn't go to the talk, but I'm willing to wait and see how it sorts itself out before believing that. Okay, so at this stage I think we've covered this first topic, which is to say that I think I've shown you that at least some very basic quantities, SU3 is close to SU infinity, and we've got linear confinement that persists to large n. So that's a sort of first step, if you like, in motivating the relevance of large n. Before moving on to talking about strings in more detail, QCD strings in more detail, let me just move to one aside, and that is to do with the running coupling. One other thing that we believe from these counting, I gave you that argument, you know, just looking at the gluon bubble, is that you should keep G squared n fixed. As n goes to infinity, up to 1 over n squared corrections, if you want to have a smooth limit which resembles the low-end theory. And that's certainly true if you look at Feynman diagrams. And it will be interesting, just nice to see that happen also in a non-perturbative calculation. So let me just show you some indication of that, of what happens. Here we have, of course, what we really have here in 4 dimensions is a running coupling. So what do we mean by this? What we mean by this is that g squared at a scale that's fixed in physical units should be fixed. Now, what do I mean fixed in physical units when I'm looking at different theories? Well, what I must mean in a sort of self-consistent way is that if I calculate something like the string tension in each theory, then at fixed values of this quantity here, so that's really L expressed in terms of the Compton wavelength of the string tension, at fixed values of this quantity, I should find that this coupling is more or less the same as I increase n. So that would be a way of testing this. Now, how can I do that? Well, there are, of course, good ways to do that. And one of the good ways to do that would be to do the kind of very nice calculation of the running coupling that has been done by the Alpha collaboration in the 90s. A beautiful calculation that produces a running coupling on the lattice in the case of SU3 that spans a range of energy scales as large as experiment and is more accurate than experiment. So it's very nice. However, that's a bit like doing this 3-loop calculation we heard about in the last lecture. It's hard. So what instead I do is do something what we call cheap and cheerful, which is use a coupling which is okay, but not as good as that because it's really defined on the scale of the lattice spacing. I go back to the Baire coupling. So let me look at the Baire coupling. Remember, we have our parameter beta is twice n over the Baire coupling, which is some running coupling defined on the scale A. And I extract this value. At each calculation, I've got A root sigma. So I can plot, I can see what is g squared A times n when plotted against A root sigma. And the question is, do you get a universal set of curves for different n's, from different n's? Now, I don't actually do it with this g squared because it's known, this g squared is notorious for being a bad coupling in the sense that if you calculate the lambda parameter and compare it to a sort of standard scheme like MS bar scheme, there's a factor of order 50 between them, which tells you that there are large higher order terms in the renormalization group equation for this kind of coupling. And there are various fixes for this, but a fix that, for other reasons that I could go into, is a nice one, is the mean field one, where you improve it by multiplying by the average plaquette. So gi squared, but let's not go into these details. Gi squared is equal to g squared divided by the average of the plaquette. 1 over n trace in P. So that's Parisi's mean field improvement from the early 80s, and it turns out actually to be a good improvement for reasons that I could go into, but I won't. But if people want to ask me later at some point, I'm happy to do so. So let's look at this, and what do we find? Do we find a single universal curve? Well, pretty much yes. So from all these calculations that I've done in SU2, SU3, SU4, SU6, and SU8, given them different little points there, and you look at g squared of the lattice spacing, the Baire coupling, improved in that way times n, and you plot it against A root sigma, which is the value you get in each one of these calculations for A root sigma, and you see that to a very good approximation, sort of lies on top of each other. It gets better as you go to smaller lattice spacings. At larger lattice spacings, here, coarser lattice spacings, the deviations between, say, SU2 and SU8 are larger. But even here, though, they're still not enormous. As soon as you go to SU3, they're smaller, and then they lie on top of each other after that. So this is sort of, I think, decent evidence, extra evidence if you need it, not from a completely non-perturbative calculation, that that this is the limit you want to take. That this g squared n is fixed, as n goes to infinity if you want to keep the physics fixed. I mean, discussing this is a little bit complicated by the fact that it's a running coupling, not a nice. I mean, if you're in 2+1 dimensions where you don't have to let the coupling run at all, it's a very simple discussion. It's just a g squared n. There's no running, no scale. Okay, so that's one aside. I suppose I should mention here, and you might be actually interested to know how this coupling, can you fit it by some typical perturbative formula, this kind of running coupling. And then, of course, there's another question that arises, and that is, at some point, if I'm trying to fit it by a perturbative formula, at some point I'm going into the strong coupling regime, where a perturbative formula doesn't apply at all. All the expressions I've shown you, including my order a squared corrections and so on, have been in a weak coupling limit. So it's important that you stay in the region where weak coupling expansions are valid. Now, it so happens that in the SUN lattice gauge theory, there is a nice phenomenon which tells you, at least at larger n, when you are in weak coupling. And that phenomenon is a phase transition between strong and weak coupling. So here is a plot of the string tension calculated for various values of this parameter beta, 2n over g squared, where g squared is our bare coupling. Here we're certainly in weak coupling here, and here is where we typically we use these points for our fits to the continuum limit. However, you can go back to stronger coupling, and when you go to stronger coupling, you find that you smoothly go on to the strong coupling expansion here. And in between somewhere here, you've got some kind of presumably the description of the variation is neither strong nor weak coupling. One of them is an expansion in 1 over g squared here, and here is an expansion in g squared. So it's not clear at what point you should really be trying to do a weak coupling fit here.
Is there evidence of anything non-analytic going on there?
Not here, no. Not in SU3. But in SU, as soon as you go to larger than SU4, you find you have a first order phase transition. This would vary according to which lattice action you're using. Right. So here you see the same plot, and here you see a metastable region. If I come from here, I go along these dark points, and then I jump up to here. If I come this way, I go up to here, and I jump down here. And it's a huge, strong first order phase transition between the weak and strong coupling regions, which is very nice because it then this is really weak coupling here the whole way, while up there it's some kind of strong coupling. And this is an analog, this is the 3+1 dimensional analog of the Gross-Witten transition in 1+1 dimensions, where you also have a phase transition, in that case just at infinite n, between the strong coupling expansion and the weak coupling expansion. And in this case, I've sort of plotted it slightly differently. There's an exponential of the string tension here, rather than the string tension
you
itself.
believe this would still be a phase transition at finite n in infinite volume? In your case?
Sorry. Yes. This certainly would be a phase transition at finite n in infinite volume, as far as one can tell, unless there's sort of exponentially small corrections that prevent that, which we couldn't see. But certainly that's the way it looks, as good as any phase transition, first order transition. It's only now when you go to infinite n, then you would have it on finite volume as well. So, but that's so it becomes sharper. It becomes sharper as you go to larger n, because the sort of latent heat across this transition is order n squared.
Can you characterize the transition? Is there another quantity that would serve as an order parameter for the transition? Is there some difference in symmetry, or?
Well, I'm less sure of that, although I'm less sure it's not, I can't give, it's, however, some of these phase transitions have been characterized, these kind of bulk transitions, and especially if you look at them in an extended coupling plane where you can put in couplings, not just, I mean, here we've got the plaquette action, but we could also put in essentially an action to the adjoint representation where we plaquette squared and so on. You can put in other terms, which in the continuum limit would be equivalent, which would be the same, but locally they're different. And what you can, there's an interpretation of these transitions in terms of condensations of Zn vortices. So I think it's, I wouldn't be able to give you a very straight off a clear recollection of that, but there are interpretations in those terms that basically when you go to strong coupling, it's easy to have plaquettes which are -1, so that's like Z2, well, in SU2 would be Z2 vortices you could have, and Z2 monopoles at the end of these vortices, and so on. And then as you go to weak coupling, these get killed off, because the plaquette gets closer and closer to +1, so you don't get large values, negative values of the plaquette. And then, of course, you can discuss Zn vortices in SU n-gauge theory. So I think one can think of them in those terms, but I wouldn't want to carry it any further right here, because we could talk about that if you like, if you're interested.
Can I just make sure I've understood? I was taught as a student that one way to prove confinement is to show there's no phase transition between strong coupling expansion and weak coupling. That's not true. There is.
Well, I mean, it's certainly if there is no phase transition, then you have demonstrated.
That statement's still true. But
it's still true, but it's only true in the sense that another scenario is that the string tension goes to 0 in physical units as you go to the continuum limit. That could have happened, and you would never see a phase transition at finite coupling, but it would have effectively been a kind of complicated transition at infinite coupling. So that argument was always a little bit fluid, if you like.
That's moot now. You're telling me there just is a phase transition.
There is. However, at finite n, if I'm in an extended coupling plane, I can go around that phase transition. There are in these other couplings. So I can go to the continuum limit and around this. There is still a continuation, smooth continuation around it. If I stay on this one axis where I've only got this plaquette term, then I can't do that.
No phase separation.
There's no phase separation, exactly. There's no phase separation. At n equals infinity, I believe it's the case that this phase transition goes all the way down, and there may be a phase transition. I'm less certain. It depends how you extend your couplings. So that's
the other couplings are going to be different actions, all of which reduce to Yang-Mills.
Yeah, exactly. Different representations. Yeah.
So then this comes back to the next question. If there is an order parameter, some condensation of Z and vortices, you no longer have that argument either.
Well, okay, I'm not sure about that. Yeah, I don't want to. I didn't want to go any further into that argument because I think it's a little bit. In SU2, that was the argument used. In SU3, it becomes complicated anyway when you talk about Zn because then you've got many more vortices that can condense, and they would naturally condense at different values of the action because they have different action themselves. So one has to rethink the whole argument. And somehow at n equals infinity, talking about vortices is wrong because. I mean, all these arguments you have at low n for confinement or anything else, which is in terms of topological objects, disordering the vacuum, and these topological objects are spread out in space-time, it really has in mind that you have an ensemble of gauge field configurations which disorder the Wilson loop. At n equals infinity, you have one gauge field configuration, so those arguments can't work, really. I mean, all the disorder has somehow to be embedded in the n-line matrices rather than in space-time. So actually, I shouldn't even, maybe the vortex thing is irrelevant for large n anyway, for that reason as well. So but that's, yeah. Well, actually, when you see some kind of, so here what we have is a weak coupling phase I emphasized, but we also have a strong coupling phase that extends to quite far. And you might ask yourself, is there something, you ADS CFT guys are always talking about strong coupling. So, and there's no point going to really strong lattice coupling to compare because there you've broken all the rotational symmetries. You've got a lattice spacing which is much bigger than your Compton wavelengths. So it's it's just totally distorted. It's completely non-universal. By the time you get here, there's some evidence that you've restored to some extent rotational symmetry in the strong coupling phase. I just sort of looked at that very, without too much care. But there seems to be some evidence if you look at the dispersion relation. And this is a very crude calculation of dispersion relation for something like a typical object in the theory, like a glue ball. The red points show the E squared, and here's P squared, and this will be the dispersion relation in infinite volume for E squared equals m squared plus b squared, well, in a continuum, I mean. And you get something which begins to show some behavior like that, and maybe if it certainly improves if I replace this by a sine function here, which is what you might expect on a periodic lattice. But it's just a hint that there might be something more physical. And the point being that it may be that you have, while you're still in the strong coupling, you may have already gone past the roughening transition here, so that you've effectively restored some of your rotational bearing. You've effectively restored rotational bearings and so on. I'm not sure about that, but that's I'm trying to tantalize you with possibilities in that particular case. But it's such a rough calculation. It's always dangerous. I mean, that's, with lattice calculations, you get something very rough, and it looks very interesting. And then very often when you do it carefully, you realize that you shouldn't have been so interested. Okay. Before moving to strings, one last little comment. I was reminded during some of these lectures by that. Here I just showed you the coupling, G squared n. Okay, it's a particular coupling in a particular scheme, the lattice scheme, the bare coupling, but other values in other schemes wouldn't be that much different. And this is in the weak coupling region. And for those of you who paid attention, would have noticed these numbers here. So G squared n in the weak coupling region, indeed the smallest coupling I ever go to here, is about 4.5. So that's weak coupling. And the reason, and of course you then think to yourself, well, is that really very physical? And of course you realize it is, because you realize the normal calculations of the strong coupling at the Z mass are about 0.1. And this thing is of course G squared over 4 pi. And if I turn it into n times g squared, I have to multiply by 3, because then you see 3 here, times 3. So 3g squared is 0.1 times 12 pi. So indeed it's around 4. So at the Z mass, g squared n in the real world is around 4. Now whether that makes you happy or not as ADS CFT people, I'm not sure. Clearly, in perturbation theory, are factors of 4 pi squared always, or 16 pi, or 4 pi, or 4 pi squared, or 16 pi squared in many calculations, dividing the g squared. So that's why it can be a nice perturbative expansion, even though g squared n is quite large. So it's, I think obviously g squared n, when you say g squared n is large in ADS CFT, you must be thinking of a much larger value, I suppose. Or maybe you don't have 4 pi. Infinity, yes. But sometimes you sort of, especially in a finite, okay, yeah, okay. But just mention that because weak coupling is g squared n of around 5. So one should remember that. Okay. Let me just begin talking about going on to the second major topic I wanted to cover, which is some string calculations. So essentially, it's looking at strings around a spatial torus and trying to calculate as much of the spectrum as I can, not just the ground state, the lighter string, which gives me the string tension, but also the excited strings. And seeing how, and then varying L, and seeing at different L's how it compares with simple string model expectations. So that's going to be the next thing I look at. And let me just say a few words right now about that, and then I'll continue next time. So this is really an old idea that if you have a long flux tube, you should have some effective string theory describing it. Of course, you always run up against the fact that it can only be a sort of very effective string theory, presumably, because you know that in 4 dimensions you don't have, directly speaking, you don't have consistent string theories. You'd have to go to 10 or 26 dimensions. Well, 26 for bosonic strings, so which is probably what we're dealing with here if the massless modes are all bosonic. And so you might wonder whether this is possible. And now it's true that confining flux tubes, we don't really know their dynamics well because there's a strong coupling theory. However, there are other theories in 4 dimensions which are weak coupling and have flux tubes, have strings effectively, like Nielsen-Olsen vortices in the abelian Higgs models. And there you can analyze, and there you know you have strings. And there's no doubt about it. These things are weak coupling objects. So we do know that we really do have strings in four-dimensional theory, so we should be able to describe them with effective string theories. And how that might happen, there have been various comments in the literature over the years. One of the comments I just mentioned here, which goes back to 1983, typically, well, there are various inconsistencies that arise when you quantize free-bosonic strings in four dimensions, and one of them is a breakdown of Lorentz invariance in a certain way of quantizing. However, if you look at the generators of rotations, the breakdown of the rotational variance arises that you have some anomalous term there. However, in the Arvis calculation, when you look at this anomaly, it goes like 1 over r squared, so it disappears at long distances. So again, that gives you a strong indication that you should be able to discuss long effective string theories of long strings consistently. This was a comment made by Olson a long time ago. So there should be some kind of effective string theory, and of course we would like to be more ambitious, and we're, on the one hand, we're trying to look at it in terms of an effective string theory. On the other hand, we'd like to provide useful information for people maybe looking in a much less direct way at strings in four-dimensional theories from the idea CFT side. So in the last few minutes, I just mentioned some of the different ways people have analyzed this problem. There is an analysis, the oldest, I think, systematic analysis goes back to Lucia, Szymanczyk, and Weiss in 1980, pursued by Lucia, and then much more recently. So this is a classic paper that I think most of you will have heard of. This is something more recent which may have passed many people by. So they were probably the first people to sort of discuss the fact that you have if you have an effective, what they did is they discussed the theory in terms of the transverse fluctuations and treating an effective field theory for those transverse fluctuations. So you have a long string, you have oscillators which you quantize for the vibrations of the string, and the zero modes give that Lucia term that we saw a few minutes ago, the 1 over L correction, and that depends on the massless modes. The coefficient depends on the massless modes, and that's fixed if you think that the only massless modes are the transverse oscillations. So, and then you can discuss possible interactions amongst these oscillators in a general sort of field theoretic way. You just set up the oscillators and have and consider possible interactions and try to constrain them by any symmetries that you know in this framework. And in particular, the kind of symmetry that turns out to be useful is an open-closed string duality, useful in this more recent paper. So if I have my Podyakov loop here, if I have my static charges going around the torus, I can either think of the strings as being attached to these charges and going this way, so I have a spectrum going this way. I can write my partition function with these sources as a spec in terms of the energy eigenstates of the strings going this way, or in terms of closed strings going this way. And that introduces some constraints, which turn out to be moderately powerful, enough, in fact, to actually lead them to the conclusion that the next term, not just the 1 over L, but the 1 over L cubed term, is also universal. Beyond that, they haven't been able to go, and I understand, talking to Peter Weiss, that beyond that, the calculation becomes difficult, three-loop type of calculation rather than maybe worse. But it's possible, but difficult. It is and the other kind of approach people have taken has been a covariant effective string theory approach. It's a more recent one. It was there was this discussion by Polchinski. It's based on the discussion by Polchinski and Strominger about 16 years ago, where they again addressed this question, but they addressed it in a covariant way. And that led them. So what they said is, you start off with an action which is proportional to the area, and there's some integral and you imagine integrating out all the massive modes, so you're just left with a massless one. That gives you the action proportional to the area. But then there's a huge determinant, and they discussed what possible forms that determinant could take, and they decided to treat it as an effective action, all possible operators going beyond the sort of quadratic one, and their leading one, for example, was this term, which kind of looks horrible because it's got this funny denominator, but and it's well, so it's the same as this term here. So it's something that would diverge for small strings, but for long strings, all these derivatives are large, and if you're doing fluctuations around long strings, and so this is under control for long strings. So it's again a calculation that's good for long strings and looking for corrections effectively as inverse powers of L, and they can constrain higher order terms by asking that there should be no conformal anomaly. So you want conformal invariance, that's your sole restriction, and you apply it order by order in 1 over L. And again, in some recent calculations, it was shown by Drummond and then later Haridas and Matlock. They also reproduced the calculation in 2 + 1 dimensions that you have a universal 1 over L cubed, but they claim now that that universality holds for all dimensions, including 4 dimensions. Again, in this case, you can go to higher orders, at least Drummond assures me of that, but in actual fact, it's hard. So in both approaches, both the Lucia-Weiss approach and that, to go any further is a very hard calculation. It requires non-trivial perturbative calculations. Well, I think I'm probably running out of time. So, okay.
Started a bit late.
I started a bit later. Okay. So the starting point then in all these calculations will be the we start off with what I'll do is this universe, the fact that you have the first correction universal and the second correction universal for bosonic effective bosonic string theories means that it's like the Nambu-Goto, the free string theory, where you just integrate with an action proportional to the surface. And the spectrum of that is actually known, has been known for a long time. So let me just show you that, and I'll finish with that. And that'll be the starting point of comparing whatever calculations we do on the lattice of the spectrum with theory, with string theory. So this is the this is actually so here we have to this order. Okay, so this is actually the Nambu-Goto. So it's a free string theory, and therefore one can solve its spectrum. At least Arvis did that back in 1983, and this kind of expression appears now in string theory books. So you have, and it's an expression where you have the energy squared, this kind of covariant form, times sigma L squared. So this is the, if you have no oscillations, no corrections, you just have sigma L for the energy. This is the first piece. Then from the oscillators of different wavelengths, you get, on your string, you have left and right moving oscillators. And these left and right moving oscillators had better, their total momentum, they carry momentum. So if your string has 0 momentum, and now we're talking about along the string. So we have a string going around a torus, and it can in general have non-zero momentum going up there, this way. Of course, if it's translation invariant in this sense, then it won't have non-zero momentum because it'll cancel and be identically 0. But in general, something with a, something like that, which is not translation invariant, can be given non-zero momentum moving around the torus, and so that's one of the possible modes. And the difference between the left and right movers of the oscillator, so basically you have a string and you have phonons on it of different frequency oscillators, and you can occupy of any number for any given frequency. In the free string theory, they don't interact with each other, so you have a very simple prediction for the energy. It's just the number of left plus number of right weighted by the energies, of course. So you take this NL is the total, if you like, the total energy, left moving energy, total right moving energy, also same for the momentum. And then there's a momentum term for the string. And your state is basically these oscillators, creation operators applied to the bare string vacuum. So in this energy, this expression for the energy, you have this term, and then you have this from the, essentially it's from the oscillators, from the half h bar omega, it's the 0 point energies, give you that. So this is the simple expression for the spectrum of a closed string, closed around the torus, in the Nambu-Goto model. And that's what we'll be comparing to. If you look at the ground state has no occupation of the oscillators, so all this is 0 here, and this momentum is 0. And then you're back to something that has just a single correction, which is this from the 0-point energies, the Casimir, if you like, the Casimir energy of the string. And this looks like this now. And this is actually, comes from the energy of the background string that you've got there. And this comes from the modes, from 0-point energy of the modes, and it's like a tachyonic mass. And what you can see here, so this is the ground state energy as a function of L, and normally that tachyonic mass won't matter because it's more than counterbalanced by a much larger energy coming from the string. However, as you reduce L, at some point, this will become equal to this, and at that point the energy has gone 0, and beyond that it will become negative, and that's at that point you no longer have this corresponds to Hagedorn deconfinement in the Nambu-Goto string. So the string theory doesn't exist for string lengths less than that. On the other hand, the spectrum exists and is well behaved for any L bigger than that value. So there is a phase transition here as well. I already mentioned that you have a deconfining transition, but even if we didn't have our deconfining transition, we would have had a deconfining Hagedorn transition coming from the string theory itself.
Somehow that's to do with the size of the torus rather than the length of the string. It's just you've tied those two things together.
Yeah.
We know that there are still very short strings in the theory giving you your glue ball spectrum, right?
Right. Okay, but that's okay, but none of the yes. But of course you won't get them from Nambu-Goto.
Right.
And you won't get them from any of these approaches, because all of these approaches break down when you consider short strings.
Yeah.
So in actual fact, I should have mentioned that both Polchinski-Strominger approach and the Lucia-Weiss approach, all the extra interaction terms they introduce, they're not going to give you really interactions between strings, because interactions, suppose you're considering two strings and you want to know what is the interaction between them, that really presumably includes the exchange of small strings. And
that's 1 over n suppressed anyway.
Okay, yeah.
Be interested in that, but
well,
leading order books.
Well, I'll be coming to that when I talk about K-strings, where they are indeed, they are the interaction.
Oh yeah, of course, that binds them.
It binds them. But certainly for glue balls, you have small closed strings. So I don't think, well, okay. This whole discussion, of course, if you take, the only place where you could take the Nambu-Goto theory entirely seriously would be at n equals infinity, because it's a non-interacting string theory. And you know that at finite n, you will have interactions. You know, for example, that an excited state, which is quite an excited string state, can decay into a much lighter string state by emitting a glue ball at finite n. At n equals infinity, that no longer happens. So certainly you know that Nambu-Goto cannot be completely right at finite n, but it might be a lot better at infinite n. And so one of the things we'll be trying to do is to see whether, how good is it as a function of n, as well as a function of L.
My point was just that the string theory should exist for the small strings.
Oh, so okay. So
it won't be described in such a simple way.
Yeah. Okay. That's right. But I was thinking of strings closed around the torus.
Right.
You can still have small strings.
Smaller then.
Yeah, you can still have strings which are smaller. And of course, if you're talking about an approach from ADS-CFT side, then of course maybe that creates new possibilities. Yeah. So I was just making the point that when it becomes small enough, the strings wound around the torus, when you make the torus small enough, you lose effectively, basically what happens is like deconfinement, you just get huge wiggles in your strings and they become infinitely larger, condense in the vacuum, and you no longer have a description in terms of isolated strings that you can discuss. Well, I'll stop there. This was just, what I've done just now is to say something about some of the theoretical approaches and background to considering what might be the spectrum of strings of QCD flux tubes. And I thought that the best way to deal with that question was by considering that sector of the theory which consists of flux tubes wrapped around a spatial torus. We look at that, we're going to look at the spectrum of those, and we're going to try and see whether it looks like a bosonic string, and whether it looks indeed like a non-interacting bosonic string, and if not, where those, what are the differences? So that would be what I'll talk about tomorrow morning.
Any more questions, Mike?
Well, in the last slide, you said that the tachyon could point out to a Hagedorn behavior at the confinement transition, but the tachyon which points out the Hagedorn behavior for the transition is a tachyon coming from a string winding Teter. So that tachyon was like the instability of the vacuum, from string theory. I didn't get the point. When
well, let me just, okay, so the point, suppose I'm really looking at a setup for confinement. I have a short Euclidean time direction. I look at Polyakov loops, which give me the effective potential as a function bar here, V of r. And at large r, so here the L in this direction, Lt, let's call it, is 1 over temperature. This V of r at large distances will be some effective string tension as a function of temperature times r, right? If you have linear, so I'm still for t less than Tc. And now, so this I calculate. When I calculate this, I calculate it from correlations of Polyakov loops. But what I'm interested in when calculating the potential is I'm interested in the energies of states going this way. However, that's equal by open-closed string duality. That E equal to the sum of things going this way. And if I make R large enough, the correlation function here is dominated by the lighter state. And if the energy of that lighter state goes to 0, as it does at this point that I call the Hagedorn transition, then the effective string tension is going to 0. They're just equal to each other if you write it down, because I'm essentially saying the product of Polyakov loops is equal to e to the V of r times Lt for if I make this very large here, and this has this form, but also if I look at it in terms of energy eigenstates going this way, it's equal to look at it this way, the separate. I'm looking at transfer matrix going this way, and r is the distance it goes, and it's equal to sigma times Lt. E times the energy of the flux loop going around here, which is a function of Lt times r. These two expressions will be equal in the limit where r becomes large for fixed Lt. And therefore, the effective string tension as a function of temperature can be obtained from this energy of this winding state here. And if that energy goes to 0, as it did, that means the effective string tension is going to 0. And in that sense, it's a deconfinement transition. The string tension goes to 0 between these sources, which are whose propagators are the Polyakov loops. There are two different ways of looking at this kind of setup. You can either look at it in terms of states going around the torus this way, and they're hanging onto sources, or you can look at it in terms of flux loops going this way between these two operators. And if the lighter state this way if its energy goes to 0, that will tell you that the effective string tension here also goes to 0 for asymptotically large r. The asymptotically large r is what you need in order for the lighter state going this way to dominate the calculation of these particular loops. So that is, okay, so that's why, and when I say Hagedorn, well, the Hagedorn transition, I use that in the sense of we have in mind that these, in any string theory, at some point, the number of ways you can put a string in space overwhelms the Boltzmann factor sigma L over T. So the number of ways you can put a string is some gamma to the L, and if you like, e to some constant times L. And when t becomes large enough, the entropy factor will always overwhelm the Boltzmann factor that suppresses strings, and then you get a condensation of arbitrary long strings. And I was kind of identifying that naturally within the Navier-Goto, and I think it's correct with that particular instability, as you say. Of course, the string theory itself, doesn't know about the deconfined phase. So when I call it deconfinement, all I'm really saying is the effective string tension goes to 0. It doesn't know about the deconfined phase because all it has is a confined phase, and then beyond that is a bit of a mystery, I suppose. In the real world, there are things beyond that. There are these multi-gluon states that don't appear when you talk about the confining phase, but they're there in the partition function, although we ignore them at low temperatures. And as we increase the temperature, they become more important because they have an entropy going like order n squared. So at some point, they overwhelm things, and you go bang into this separate sector of states, which is composed of states where you've got a finite number of gluons per unit volume. And this sector of states is your deconfined phase. But that you don't see in the string theory. So I was using the word deconfined kind of loosely, but in the sense of string tension going to 0.
We're very late for coffee, and it's getting cold, so maybe we could have this discussion in the discussion session or over coffee. Okay, let's thank Mike.